Bom dia, vamos começar a aula de hoje. So, today I'm going to talk about Hodge cycles and transcendence. Okay, so let me remember one few stuff about Fermat variety. So, as I said, we are always working with the affine Fermat variety equal to 1, and then we can put here S. The formulas can be written for this one in an easy way. So we are dealing with this affine Fermat variety, and so I introduced these differential forms 1 n plus 1 and omega beta, which is x beta. In our context of Fermat variety, this actually this eta beta omega beta is the same. So let's write the n form. So it was a equal to 1 until n plus 1 minus 1 to the I xi, the wedge product of all dxi except dxi itself. So this was our differential form. So as I said in the previous, so for the de Rham cohomology of the compact, so let's say if this is L is inside the compactification, and then this is inside Pn plus 1. For the de Rham cohomology of X, we will need, we can remove, let me say, so I have to define A beta. A beta was beta I plus 1, D equal to 1, n plus 1. Okay, so we are just interested in I beta less between 0 and 1, I beta is strictly between 2 and 1. So I beta integer were corresponding to the Hodge structure of the compact, the divisor at the infinity. And something else also, that omega beta prime integrated our cycles delta beta. Maybe I write it in our context again, minus 1 to the n d to the n plus 1 beta 1 prime plus 1 d beta prime 1, n plus 1 plus 1 d. This apparently transcendental factor, and then the algebraic factor I equal to 1 n plus 1 zeta d minus zeta d here, beta I plus 1 beta I prime plus 1, and then over here beta I prime plus 1. So then they basically, using this data, we can a little bit do Hodge theory. So maybe one first observation. This is not written explicitly in my book. So the Hodge cycle. So maybe I think, let's say, affine Hodge cycle. What they were cycles delta such that omega beta equal to 0 for beta in I. So remember that I was in our case 0, 1, d minus 2 to the n plus 1. And a beta, we always avoid integers, and then a beta is less than n half. So anyway, if I make, so this, there is this, the middle one, the middle block is n half plus 1. And so everything here the integration of all differential forms until here, they're all 0. And okay, so maybe one observation that I want to make. So this is the characteristic of the Fermat variety, but for this differential form, the integrals are also 0 for a Hodge cycle. So let me say omega beta delta, let's say delta is 0. So of course a beta less for them not integer, and then a beta bigger than n half plus 1. And the reason is that maybe I explain in a few words. Let me. Well, the reason is that if you make the complex conjugate of this formula, let's take the complex conjugate. So these are real numbers. So the only complex numbers which appears is here. So you will have a complex conjugate also here. But the point is that zeta d bar is what? It is zeta d, let's say minus 1, minus 1. Let me see, because zeta, exactly, zeta d zeta is of norm 1, and this is zeta d minus 1. This is zeta d is the root of unity. And so if you use this one here, and then you use let's say the Rham theorem, then omega beta prime bar in cohomology, it will be omega d minus 2 minus beta. So this means that d minus 2 minus beta is the same as saying that d minus 2 minus beta 1, d minus 2 minus beta 2, blah, 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 and so d minus 2 minus beta n plus 1. Oops, sorry. And so you just replace this one here, and take, let's say, and actually, let's say, use this one here, minus goes to beta I primes, and then you add the factor of d, and then you will get this fact. And the point is that then you will realize that this a d minus 2 minus beta is the same as when you compute it, it's n plus 1 minus a beta. And then you use if omega beta over delta is equal to 0. This is the same as omega beta bar delta over 0. And then the moral of the story is that n half plus 1 integrals are 0. When you take bar, then you get here, and so the integrals here also will be 0. So, but this is not a general phenomenon. This is actually, for the moment, just for Fermat variety, where the periods are up to some constant transcendental factor. They can be expressed in terms of the root of unity. Okay, so this means that at the end, that the only non-trivial integrals that we have are for differential forms omega beta with a beta n half plus 1. And at the end, this is a basis of h n half, if I want to use the modern language of the compactified Fermat variety. And actually I have to say that it's a primitive part. This primitive part always is one dimension less than the the actual and half-half. But at the end, just working with the primitive part, we can capture all the discussions for the usual one. Okay, any case, so maybe one proposition. So let's say a space of Hodge cycles. Again, just not to bother oneself with integrality. It actually, this is important, but and then the primitive one, then the map, let's say to, so let's say the dimension of this one, let's call it h and half 0. And what is this? This is the cardinality of beta in I, such that beta, these are they form a basis, and half plus 1 and half. This is the one of our Hodge numbers. So this number, we call it h on and half primitive, and maybe h and half primitive plus 1 is just the in the classic, for the classical Fermat variety, it's just n half. Anyway, if we don't want to bother ourselves with the modern language, it's just, for me, this number is just the cardinality of this omega beta. So let's take h and half. So to a cycle, we associate the vector omega beta delta. So here the vector, the beta is varying in I and beta between n half plus 1 and half. Okay, so this is one observation is that this is an inclusion. Is an inclusion. So this is an injective, well, I take a injective map, and the proof is just the theorem up to this polarization factor and this primitive part, this discussion. It is just the de Rham theorem. So if delta goes to 0, then what it means, if delta under this map goes to 0, then this means that omega beta delta is 0 for all beta in I, beta not integer, and so this means that my integral is 0 for all these guys, and even the middle one. But we know that omega beta, let's say these guys, omega beta, these guys form a basis for h and de Rham, let's say x primitive, and since delta is let's say, so the point is that we have taken tilde delta is supported in L. So as I said, we always take cycles in supported N. This means that delta actually, then I have already written here. So anyway, I don't need to this discussion. So the point is that we have a de Rham theorem. We have de Rham theorem for this primitive part. So h n x q primitive, H and the Rham X primitive, the integration, so the let's say delta and omega going to integral omega delta. So this is a non-degenerate, but so if all the differential forms of our delta are 0, then delta must be 0. So this means that then this will imply that delta equals 0. Anyway, the de Rham theorem for X compact will implies the de Rham theorem for the primitive part. And then this theorem basically follows from this one. So the moral of the story is that I will call this one a periods of the Hodge cycle delta. And the periods of the higher Hodge cycle delta, it determines the Hodge cycle uniquely. So from now on, we are going to discuss a little bit that these periods, they contains a lot of arithmetic data, a lot of arithmetic and algebra geometric and what else? And transcendental number theory stuff. Okay, so any question? Okay, so let me see which lecture I mentioned the Rham. Okay. So remember, let's say this is theorem 61 in my book that actually it is due to Delin. Maybe, okay. Well, in our context, omega beta. So maybe let's just use the omega beta delta. So always the classical Fermat variety. Let's say primitive Hodge cycle. This number, so the integration is always an algebraic number for, of course, a beta not integer, a beta between n½ plus 1. So the moral of the story of this theorem is that periods of Hodge cycles, they have only one transcendental factor, which is a 2 pi I to n½, and then some algebraic number. And this is this turns I have to say this takes Hodge theory into a more transcendental number theory discussion. And actually, we have already proved this statement. At least most of the proof we have done. No, we have not. Well, let me see in this way. Observation, Hodge conjecture implies the above theorem. This one we have done basically, and maybe one reason why Hodge conjecture enters into transcendental number theory. So the Hodge conjecture implies the above theorem. Let me explain a little bit this one. So if so maybe I want to now explain the reason for this observation. So let's assume that the Hodge conjecture is true. Hodge conjecture for Fermat. So the main point is that at some point I will explain Shioda's work, how much we know about the Hodge conjecture for Fermat, but for now we don't know if the Hodge conjecture is true for Fermat or not. And the point is that still the Hodge conjecture for all Fermat varieties of all degree still is a big open question. So look, so let's try to understand this. So let's delta. So if the Hodge conjecture is true, any Hodge cycle is an algebraic cycle. Okay. Z Zi inside X and the dimension of Zi and half. So if the Hodge conjecture is true, then we will delta will be supported in algebraic cycles. So since we are working over with the just homological class of algebraic cycles, so it comes from the next step. We can assume that Zi's are defined over Q bar. This is I will not explain too much, but if you want, we can talk about this one. So the point is that the Fermat variety is still defined over Q. So the point that X, the Fermat variety, is defined over Q. So if by sudden you find some algebraic cycles, maybe I explain in this way. If you have your Fermat variety and you have the suddenly you find some algebraic cycle inside it. And if it is not defined over Q bar, this means that it is defined over some extension of Q bar. What this means? This means that you have used transcendental number in the defining equation of Zi. But with a little bit effort, we can transform these transcendental numbers into variables, and then it turns out that the Zi becomes in a family. And this family is defined over Q bar, and then we define a member of the family which is with coefficient in Q bar. So this is at some point I can start explaining this phenomenon. And but for now, just a kind of curious fact that whenever we find some algebraic cycles and we are just interested on the homological class of that algebraic cycle, then we can assume that such an algebraic cycle is defined over Q bar. And then it comes from the next fact from the lecture 15. After doing algebraic de Rham cohomology, remember that we proved that omega over Zi 1 2 pi I. Then let's just use our differential form and half their algebraic number. So differential form, they themselves are defined over Q. My Fermat variety defined over Q, but my algebraic cycle is defined over Q bar. And then we proved using algebraic method, the Rham homology, this fact. And then it is finished because if the algebraic cycle, well, we replace delta with algebraic cycles, then we can use this one. So the point is that there are three steps. First, assuming the Hodge conjecture. Second, this one is not so difficult. And the third one, that the integration over algebraic cycles does not produce the transcendental number if the algebraic cycles are defined over Q bar. And this argument proves that the Hodge conjecture implies this one. But of course, it is desirable to prove this statement independently, and Delina has proved this one independently of the Hodge conjecture. Today, I will try to talk about this a little bit. Okay, so any question? Okay. So let's go back to the structure of our integral. What time? So let's b beta. Remember, let's define b beta 2 pi I minus n half, and this beta factor. Let me write the beta factor, gamma beta 1 plus 1 d gamma beta n plus 1 divided by d, and then gamma of sum of all these, which was this just a beta. So a priori, you see that this must be some transcendental number. I mean, the values of gamma factors are in general transcendental numbers. So by looking its expression, there is no reason that this guy to be an algebraic number. And so, and remember, so this will let me go to so continuation of the Lenz's theorem. So the so let me again omega beta. So delta is a Hodge cycles 2 pi I n half. This is the same as here. So this is b beta times some number a. Felipe. Deixa eu ler aqui. O Matheus está falando alguma coisa, tá?
Tá cortando.
A voz ou...
Também. Mas.
Deixa eu ver. Você está me ouvindo bem? Felipe, você está me ouvindo bem ou não? Bom, deixa eu ver. Ok, eu vou continuar depois. Você está me ouvindo bem ou ainda continua o problema? Tem algum problema aí? Bom, vamos. So, this integral is of this format. This is in Q bar. So, and let's say so either b beta is in Q bar. So this is some probably transcendent number, and this is some algebraic number. So or this or this a is 0. This means that omega beta delta equal to 0. And okay, so maybe again I say that what's the moral of the story here. So we realize that for beta, strictly between this one, so Tá completamente travado. Felipe, se vocês querem, saiam uma vez e entrem mais uma vez para ver se funciona. Eu acho que deu bom. Isso, é melhor sair e entrar mais uma vez para ver. Felipe, tá. Agora vamos ver que se... Tá, então, tá bom, vou continuar então. Okay, so the point that we have this differential form beta, omega beta, with beta between n-half and n-half plus 1. So the integration of the differential forms over the Hodge cycle must be either 0 or this b beta must be an algebraic number. So, and remember this, you look at this b beta, there is no reason to be an algebraic number. So okay, so let's try to see that this theorem of Berlin, it reduces to some let's say some elementary, let's say, number theory. Okay, so let me proof. Okay, reducing Berlin's theorem to an elementary problem. So anyway, this is not a proof, but what I'm saying that at the end, this elementary problem, you can you don't need the topology, you don't need Hodge theory. With just some basic knowledge of working mode primes, you can start thinking about this one. Okay, so let's start to do this one. Omega, let's define omega beta. Check this omega beta divided by this b beta factor. So, and b beta factor, and actually there was this rational number also, but this rational number will not produce a problem. At the end of the day, this is remember that omega beta check our delta is this, basically this number, I equal to n plus 1. Remember this beta I plus 1, beta I let me no our algebraic cycle, but okay, no, because I have not. Anyway, we know that this is we have explicit formula that is an algebraic number, and actually number in Q zeta d. So at some point we started to do Galois theory, the complex conjugate, but we know we'll use this now Galois theory. So Galois Q zeta d over Q. We know that this is just the invertible elements of z ddzt. This is invertible elements, and so for example, this sigma corresponds to what here? This let me say zeta d, or maybe let's, if you have invertible elements here, the corresponding Galois elements is just zeta d going to, maybe let's put p zeta d to the p. Anyway, we have a good knowledge of this Galois group. Okay, so the basic things that I want to make, I will take sigma from the Galois group. So sigma will be identified with p. And maybe before going, okay. Okay, so we can define this sigma, the differential form omega beta check. Here, actually, the delta is an arbitrary cycle for the moment. I can define by de Rham theorem just based on this this omega beta check over delta. So this is remember that this is an algebraic number, so I can take sigma of this one. This will define a map from homology to complex number. So there will be a differential form which will represent the integration over delta, and so we will get this one. So for this one, we use again de Rham. We use de Rham theorem that the homology is dual to a cohomology to define this guy. But the point is that when we do this one, we can actually compute this one. So let me say at the end, if delta is delta c beta delta beta, maybe we don't. I don't write this one, but what I am going to say, we can compute this sigma omega check. It will turn out to be omega some operation p star on p. And what is this operation p star? P star beta is, maybe I just write a p times beta 1 plus 1 minus 1. Let me see, and it's integer, and so on. So let's start from here. P star beta, p some invertible element that in z dz. Here you just multiply p plus b plus 1, and then take integer part and then minus 1. And then we have this equality, and this equality, let's go back to the formula and to see that why this equality. First of all, my Galois group sigma acts, it takes zeta d to the zeta d to plus zeta d to the p. And then when I act this Galois group on my integral, where is the formula of the integral? Okay, you see, the integrand appear beta I plus 1 prime, beta I plus 1. So this p will go to here, and then we can, I will write it again as integration of differential form. That's why at the end we reach to this this formula. Okay, so so we have this formula, and it is now okay. So what is now our elementary problem? Maybe I make again the picture and half, and then omega betas. I started from omega beta here, and then the point is that I took invertible element P, what am I doing? Okay. So then I will let this group act on this omega beta, and then I will find maybe omega p star beta. So the elementary problem which we are now trying to formulate is this one. If you do this action, and let me say in this way, okay, so if the a is less than, so if after this operation the a p star beta falls here, then the integrals of our Hodge cycles here are 0, and then we are done. But what this means? This means that we have to consider only omega betas such that, let's say, a p star beta is between n half and n half plus 1 for all p in dz invertible element here, and of course 1 is there, and then beta itself. So because if this does not happen, the integral of our Hodge cycle here are 0, and then at the end this integral that we want to prove that it is algebraic number, it's automatically 0. So so we get into this class of algebraic numbers. So, and the most probable, and the point is that most probably for these numbers the integrals are not 0. So we prove that for such betas b beta is algebraic number. Okay, so okay, and so so these are probably the transcendental beta factors, and then we are still in trouble. We have to prove that these betas are 0. But this is not really a hard transcendental number theory, but because we have a very specific combination of the values of the gamma factor. So let me say the idea of the proof of this fact. Okay, so first of all, how many functional equations we know for the gamma function? So let's write down. First of all, we know that gamma z plus 1 is z gamma z. And what else we know? We know that 2 pi I, this is Euler's reflection formula. Euler's reflection formula. 2 pi I gamma z, gamma 1 minus z is pi I z. So this is you can, if you have never seen the proof, maybe it's time to go and have a look. So we have this formula also, the gamma z, gamma 1 minus z, 2 pi I, it is e1 over e 2 pi I z minus minus e to the minus pi I z. Actually, in the classical way, it is written by sin and cosine, but this is the same formula. And another formula is Gauss. What was it? Gauss multiplication relation. Multiplication relation. What is this? Again, I write it in the form that I needed 2 pi I m minus 1, 2, and then gamma mz, and then product of k equal to 0, m minus 1, gamma z plus km. It is some there is this formula. It is equal to m half minus mz. What else? Just a moment. Z I to the okay, so this is I to the minus m1 half. Anyway, I have a little bit rewritten these formulas, but anyway, this is what I want to say, that we know this kind of functional equation for z complex number, and what else here is m integer, and actually in our context we will need it. We will need our rational numbers. So we know these relations, and so the kind of elementary, well, not really elementary, but you can try at least some examples by hand using these three relations. Okay, maybe before this one. So if z is in Q, just remember that this is an algebraic number. This is an algebraic number. So basically, when the z is a rational number, then we have many relations between the values of gamma function are evaluated on rational numbers. So using these three relations, we can check the last part of the Lenz's theorem. So the last part was what this fact. This for if we have a beta which satisfies this property, then b beta must be an algebraic number. And remember that what was b beta? B beta was just this combination of a rational number with this 2 pi I. Maybe one example that if you want to do it by yourself, let me share the screen. So that I said today, I talked about this chapter 16. Okay, this the formulas I mentioned. This this is the proof that I was trying to tell. These are the formulas of that we need to finish the proof of Lenz's theorem. And okay, let me try to what I wanted to say. Maybe let's go to the last one example at least. Where it is the exercises or okay. So what I wanted to say. Oh, sorry. I have to go to the problem. Just a moment. So let's go to this kind of elementary problem that I was mentioning. Yeah, exactly. This is the last part of the Lin's theorem. And for example, one moral of the story is that, for example, let's say we have a formula like this. So you see that dividing by this pi number, dividing by this number, we have this formula that one can check with Mathematica, but you can also check these equalities just using these three relations, the three functional equations of the gamma function. Okay, before finishing the proof, maybe I mentioned this very nice conjecture due to few people, including Delin. Moment. Oops, what I'm doing. Let's go praise of. Yeah, let's mention this one. So I want let me talk about this conjecture. Any multiplicative dependence between the values of a gamma function with rational entries, and then there are some powers, is a consequence of the standard relations. So whatever relation like this you see here. So that the conjecture says that it must be possible to derive this relation from this one, from this one, and the Gauss relation. And the point is that in the last step of the Lin's theorem, we didn't really prove this conjecture. We proved this conjecture for a very special, combination of the values of the gamma factor. Maybe it's just okay. So we proved this. Well, what I'm saying that the proof of this conjecture for this kind of betas with this property is not difficult, and it is proved actually by in the appendix of the article of Delin. This appendix is due to Koblitz and what was the other guy? Yeah. Anyway, I think for today we are done.